Our next speaker is, our next talk is going to be semi-scientific, semi-popular science, I would say, and by one of Yaakov Ziv's most outstanding students, Neri Merhav.
Thank you very much, Moti. Thank you also for inviting me. Thank you and Shlomo. I'm really excited and honored to be here today. And I'll try to compress my talk losslessly, hopefully. I'm not sure I'll succeed, but at least I'll try. Okay, first of all, a personal note. I was lucky and I had the pleasure to be a PhD student of a great giant. A lot have been said already, so I won't repeat it. All I would say that is beyond the period of the PhD, I also had the privilege of having a deep professional, both professional and personal relationship with Jacob until the last years. And he's really, by definition, a shining star in the sky of information theory and a great inspiration, at least for me, but I'm sure that for many others. Okay, so like what Professor Viterbi told us, in classical information theory, but which started with Shannon, is about the investigation of fundamental limits versus achievable performance in several examples of information processing tasks, including data compression, error correction, encryption, and many others. And it is mostly, the classical theory is based on very simple probabilistic models of IID, identically distribution, or memoryless in the language of information theory, probabilistic models, according to which every symbol of a source or every noise sample is drawn independently of all previous ones, like in fair coin tossing. So the model is a model of a channel where an information source, a message source, is transmitted, undergoes some processing, goes through a noisy channel, and then the receiver is trying to estimate what the source was. And both the source and the noise are probabilistic. The IID model is, of course, very simplistic and not very realistic. And later developments in information theory were about extending the theory to sources with memory, like Markov models, hidden Markov models, and general finite state models. That's one way, one aspect of approaching reality. The other aspect of approaching reality is relaxing the assumption that all the statistics are known, of both the source and the channel. Sorry? Okay. So in this respect, there are two approaches. One of them is robust techniques, which is about some worst case approach. I won't get into it. The other one is in developing universal methods which maintain asymptotic optimality in spite of lack of knowledge of the statistics. And this is about, we see it both in data compression and in channel coding and in other things. The more general approach is the individual sequence approach, which was greatly advocated by Jacob and Avram Lempen. So there is some hierarchy. The classical results are about known statistics, Then the next level of universality is that we don't know the exact statistics, but we know the structure. We know that it belongs to some parametric family. The next level is non-parametric uncertainty, namely we don't have any parametric structure. And last but not least is relaxing any assumptions on statistics. The data we have to compress is simply an individual deterministic sequence. So Shannon started with entropy as a notion of a complexity of a sequence to be compressed, the amount of disorder, if you will. This was in the late 40s, 48, the first paper by Shannon. Then in the 60s, these three gentlemen, Kolmogorov, Solomonov, and Chaitin, developed the algorithmic complexity, namely the so-called Kolmogorov complexity, according to which complexity of a sequence is measured according to the shortest computer program that can generate the sequence, and the program runs on a Turing machine. It's a very nice notion. The only problem with it is that it's not computable. So it's not very useful, actually, unfortunately. Then came the second notion of a complexity of individual sequences by Lempel and Ziv, which limited the scope not to the whole universe of Turing machines, but to finite state machines. So it's a bit weaker, but it's stronger in the sense that it's computable, and very computable very simply. So here's how it looks like. The finite state encoder is a black box, which is fed sequentially by the sequence to be compressed. And it has an internal state that remembers the past, something from the past. And it has an output, and the number of states, total number of possible states is finite, it's S. And the output is a variable length binary sequence, including possibly also the empty string, which is of length 0. So that means that there are some moments that the finite state encoder is allowed to idle, not to produce any output. So here's the definition of a finite, the compressibility of a sequence in terms of finite state encoders. We have a given individual sequence, not random, a given deterministic sequence. What is the best compression ratio achieved by the best information, so-called information lossless finite state encoder with S states. So it's the minimum among all encoders with S states of the compression ratio, namely the length of the compressed file over the length of the uncompressed file, N. Now the choice of the best S-state encoder, namely the minimizer, depends on the sequence that we wish to compress by the definition. Nevertheless, Ziv and Lempel developed a universal algorithm which always asymptotically achieves the best performance, very close to rho S, provided that the number of states is very small compared to the length of the sequence. And if the number of states is of the same order of magnitude of the sequence, then our finite state encoder essentially learns by heart the sequence. It doesn't really learn anything. It's like overfitting in learning, machine learning. So how can we quantify this quantity, rho of S, compressibility? So the idea is that we parse the sequence sequentially, x1 to xn, by creating phrases, and each new phrase is the shortened phrase which has not been encountered before as a phrase. So, for example, if we have the following text, which I deliberately took it to something repetitive. What does it mean? What does it mean? What means what? Means what means what? Does means does. Means means means. What does it mean? Means what does it mean? So it's quite repetitive. And here's the parsing. So every new phrase is composed of something that we already saw and a new symbol and creating a new phrase. So, for example, in this example, the number of phrases is 44. So it's quite clear that for very repetitive sequences with very repetitive patterns, the phrases are going to grow quickly, so C is going to be small. And conversely, for non-repetitive and unpredictable sequences, there is a large variety of patterns, so the phrases grow slowly. So C is going to be very large. That's the idea. And so the main results in Ziv and Lempel's paper from 1978, what was that? Is that for S, number of states much smaller than the length of the sequence, the compressibility, the minimum compression ratio, as you remember, cannot be much smaller than C log C over N. On the other hand, the LZ algorithm, LZ78, achieves compression ratio which is not much larger than C log C over N. Namely, there are small redundancy terms. So it essentially achieves the minimum possible compression ratio among all S-state machines. So this gives rise to the notion of finite state complexity as C log C over N. That's the essential quantity. And it can be thought as the deterministic counterpart of entropy. How does it work? The LZ78 algorithm simply, each new phrase, suppose its length is L. So the first L minus 1 symbols is a phrase that we already saw, and the decoder has already decoded it. So we just send a pointer where to copy from. And the last symbol is sent uncompressed. That's it. And there are several versions of the LZ algorithm, which are all based on this idea of looking for a match in the past, string matching. And as was said already by, what's going on here? As has been said already, the Lempel-Ziv algorithm is there wherever you look. In your smartphones, in your computers, in the cloud, you name it. We are using the LZ algorithm on a daily basis without even being aware. It's also used in many well-known formats of files like PDF, TIFF, PNG, ZIP, you name it. Accordingly, in 2004, the IEEE proclaimed the LZ algorithm as a milestone of electrical engineering and computing. I'll skip this. It also has some role in physics, but I want to shorten the talk. My main point in this talk is that the LZ algorithm is useful way beyond data compression. It turns out that it can be harnessed maintaining asymptotic optimality in a large variety of information processing tasks. And this is only a partial list. And this includes hypothesis testing, model order estimation, encryption, prediction, and many others. Here's a partial list of a few papers that I'm involved in. Another aspect, which is very useful in improving the asymptotic optimality of LZ in all these other tasks, is the so-called Ziv's inequality, which tells us that the log probability of any given sequence under a Markov model or finite state model or even a hidden Markov is upper bounded, the log probability, by minus C log C. Remember, C log C is the main term of LZ compression ratio, plus some negligible terms. And this is the key tool for proving the asymptotic optimality. Of course, I'm not going to prove anything here. And it has other forms. I'll skip that. So here, I'll just end up with a few examples of this point. A very simple hypothesis testing problem. We are given a sequence x1 to xn, say a binary sequence to make it simple. And we have two hypotheses. Under H0, x1 to xn is a sequence of n independent coin tosses. And under H1, it is not. But we don't know under H1 how the sequence was generated under the alternative H1. That's what makes this problem non-trivial. Because if we knew what is the probability distribution under H1, then it's a simple application of classical hypothesis testing theory. So it turns out that the following simple decision criterion gives the best trade-off between two kinds of probabilities of error. The probability of deciding in favor of H1 while H0 is true, and the other way around. And what is this criterion? Simply compress the sequence by Lempel-Ziv, namely compute C log C over N, and compare to it the threshold. If the ratio is larger than the threshold, accept H0, because it means that the sequence is not very compressible. The sequence of independent fair coin tosses is not compressible. And if it's below the threshold, then reject it, namely decide in favor of H1. So it's very intuitive that an incompressible sequence is judged according to compression ratio. Nevertheless, it's not trivial to prove this optimality rigorously, but it's possible. Another example, well, that's quite like the previous one, so I'll skip it. Another issue in the joint work of Jacob and me in '93 is testing for statistical similarity or dissimilarity between sequences. Suppose we have two sequences, binary sequences, again for simplicity, say the two ones that you see, are they statistically similar? Well, looking at these two sequences, it appears that the answer is positive. They both contain runs of zeros and runs of ones interchangeably, and about the same length of the run. So I would say they are statistically similar. But what about these two sequences? Not so much, right? Because the left one is almost zero everywhere, while the right one is quite similar to these previous two. So can we quantify what would be a good measure for statistical similarity or dissimilarity, which could be useful in applications? So in that particular paper, we proposed the following measure. We denoted it by delta of x and y, and it involves the C log C of one of the sequences as before, but there's also another term which is C of x arrow y, which is defined as follows. It means the number of phrases of x with respect to y. What does it mean? It means find the longest prefix string of x that appears somewhere in y. There's a copy of the prefix of x1 to xi, which is an exact copy of some the same number of consecutive symbols in y. Once you find the largest I, the longest sequence, then you have one phrase of x with respect to y, and then you continue from xi plus 1 in the same manner until x is exhausted. Now, if x and y are statistically similar, whatever it means, then the phrases of x with respect to y are going to be long. I'm going to see long matches of x within y. Otherwise, they'll be short, and then the delta will be large. So here's a short example. I'll skip it to save time. And I'll just say that earlier I said that C log C over N is the counterpart of entropy in individual sequences. So this delta that I now defined is the counterpart of the so-called information divergence between two distributions. Kullback-Leibler divergence, for those of you who know the term. For those of you who don't know the term, it's not so important. What is important is that it's a measure of a distance between two probability distributions. And it turns out that this work was used and applied in a variety of contexts. One of them is text classification. The other one is EKG-based personal identification, anomaly detection, and even in statistical physics. So here's the one paper about text classification that used this ZM method, and this is about EKG, and so on in physics. Again, I'm running. It turns out that it also has, sorry about that, the Lempel-Ziv complexity has also a meaning in channel coding. Professor Viterbi mentioned channel coding before. So provided that you have feedback from the receiver to the transmitter, you can show that the capacity in the binary case is 1 minus the compressibility, like entropy of the noise, and you can achieve it if you have feedback. So here is a model of a finite state channel, very similar to the finite state model that I showed before, but now it's a channel. The output is a stochastic function of the input and the state. There is a state that is evolving here. And optimal decoding across such a channel is, we have to know the statistics of the channel. We have to know this distribution. So what do we do if we don't know the statistics? So Ziv proposed a decoding method based on Lempel-Ziv parsing. But here it is applied to a pair of sequences. One is every hypothesized channel input sequence and the channel output sequence. And basically, I won't get into the details, but basically it is a notion, it is like compressibility when you have side information, when both the decoder and the encoder have access to side information sequence that is related to the sequence X to be compressed. Y is the side information. So the decoder chooses the input sequence that minimizes this metric, this function. So it has a notion of conditional, it's like a conditional entropy, if you will. There's also a result about encryption. Again, a finite state model. We are looking for the best finite state encryptor among all encryptors with S states. Very similar definitions. And again, the result is that the so-called encryptability, namely the minimum the minimum consumption of key that we need is lower bounded by C log C over N, the entropy of the sequence, if you will, minus some negligible terms which are not important. And on the other hand, it is achieved by first applying LZ compression to the sequence and then encrypting the compressed sequence by the random key bits. So it's very similar to the probabilistic counterpart where the entropy plays the role of the minimum key rate needed. There's also results about universal prediction. Here we don't have a characterization of the prediction, number of prediction errors. Here we count here the number of prediction errors per N. And we use, the prediction is based on the engine of the LZ algorithm, and it achieves asymptotically optimal performance. This is about lossy compression, which I'll skip. And to summarize, I compressed it, I think, right?
Lossless or not?
It's always lossy in my case. So we reviewed very briefly Jacob-Ziv's individual sequence approach. The jewel of the crown is always the LZ algorithm in its various versions. And I define it as a successful marriage between a beautiful theory and great practicality. That's the slogan that I always use. We have seen Ziv's inequality and its utility. It plays a role in all the results that I briefly mentioned. I can only say that Ziv's legacy has influenced my own research journey, even until recently, and also those of colleagues and students. We have seen the LZ at the service of many tasks that are not related directly to compression, and I think that's one of the most beautiful aspects. And we've seen what I didn't talk about are extensions of the individual sequence approach to a more complicated communication configurations, including network configuration, side information, and so on. So that's about it. Thank you very much.